This is the first of two. Our first presentation is going to be given by Dana Hurley, entitled Variability of Sources of Helium in the Lunar Exosphere. Dana?
All right, can you adjust the size of the slide, please? So this is a presentation on some data from 3 spacecraft, ARTEMIS, LRO, and LADEE. And I'd like to acknowledge my co-authors here who contributed to this. Thank you, that's perfect. So the helium in the exosphere of the moon is thought to predominantly come from the solar wind. The solar wind has a small percentage of helium ions in it. And those helium ions will interact with the surface of the moon and will come out as neutral helium atoms. Some of them get backscattered immediately. With some of them will be backscatter at high energy. Some of them will get thermalized. But then you can also have those helium ions get implanted into the surface and then be released later on by subsequent sputtering. Or you can have it be implanted and then diffuse out, which is a lower energy process. But there's also some portion of the helium in the exosphere of the moon that's coming from outgassing from the lunar interior, because helium is a decay product of radioactive elements. And so as those decay over time, that helium is created and it slowly diffuses out of the moon's interior. So we want to understand the contributions from each of those sources. Now, we had a wonderful period of time of about 5 months in which we had 3 spacecraft simultaneously looking at different aspects of the system. We had ARTEMIS, which was measuring the alpha particle influx, so the solar wind contribution to the helium exosphere. We had LRO, which through the LAMP instrument was looking at the illuminated column of helium between LAMP and the surface of the moon. So it was doing a column abundance. And we also had LADEE, the neutral mass spectrometer on LADEE was measuring the helium density in situ at the spacecraft altitude as it was go in orbit around the moon. So here's a plot as a function of local time on the moon. And basically the start of the LADEE mission was here, and we're going like this in time. But we have the LADEE data at the same local time as the LRO data, and the helium density mapped to the surface of the moon. Here, right here, this is a model of what the average density is as a function of local time. And you can see that there's a lot of variability compared to that model. But when we also look at what the ARTEMIS measurement of the solar wind flux is, you can see that that tracks right along with the observations of the helium density. So it seems like the variability is predominantly controlled by the solar wind. So another way to look at that same exact question is you plot the source rate of helium measured by ARTEMIS versus a modeled source rate. So what source rate would you need in order to get the densities that were observed by LAMP and NMS? And so here are those data points. And when you perform a fit to it, you get a y-intercept right about there. And what that means is if you turned off the solar wind source, that's the density that you would expect. So that would imply that you have some endogenous source of about 30% or 36%. The slope here is 0.63, and that means there's a 63% efficiency of converting alpha particles into thermalized exospheric helium atoms, neutrals. But you know, you have these these values out here that may be really influencing your fit, and some people may say if you get rid of those, you might be able to fit a 1-to-1, or maybe you would have some intercept that's a lot lower, which would mean that it's all solar wind. So we wanted to look into this further. It turns out, even though LADEE was a 5-month mission, LRO has been at the moon for a very long time, and Artemis too. Here are similar data, but now 2.5 years worth of LAMP and Artemis data to compare. So we get very similar numbers as we got just during the LADEE mission. But, you know, you might say that, you know, if you ignore these, a 1-to-1 might look as good as the linear regression gives us. And also, if you look at, you might want to say like there's some sort of curvature to that. And in fact, both of these axes here, this LAMP source rate, there's model assumptions that go into that axis. And even the Artemis source rate, there is a model assumption that goes into that axis. So I wanted to look into those model assumptions a little bit more carefully. So starting with this axis here, the LAMP source rate, what I do is I take the LAMP column abundance and I compare that to my model of what the steady state density would be. And so say our LAMP measurement is here, I take the measured column abundance, I divide it by what the model column abundance is, assuming a certain source rate, to tell me what the inferred source rate is. And that's this number here. So if my model's wrong, I may be dividing by the wrong number, right? So if I group the data by local time, I'm dividing by a very similar number. And so here are the different fits by local time. Now, if the model is giving me the wrong source rate, you're going to get a family of curves that look like this, where you're going to get, if you're dividing by too low a number, you get a higher intercept and a higher slope. If you're dividing by too high of a number, you get a lower intercept and a lower slope. And to me, that doesn't look like what we're seeing there. So the model may or may not be right, but it's not producing the whatever thing is going on there. So now looking at this axis, this Artemis source rate, Artemis is actually measuring, as you cannot see because it's really, really faint, the instantaneous alpha flux, which you can is like this. But the instantaneous alpha flux is not a good measure of how much helium is in the exosphere, because the helium, once it gets delivered, has some lifetime. So what we did was we took this and we applied an exponential time decay to it to get an integrated amount of helium in the exosphere. So here is that value if you assume a 5-day exponential decay. And so that averages out a lot of the spiky stuff, but you still have a lot of variability left. So over here, I show what the different fits would be for different assumptions of that decay rate. And so you can see as you go to longer decay rates, what you get is a lower intercept and a higher slope. So that led me to want to apply a time-dependent model to the observation. So I have a model where I follow the helium atoms as a function of time, and I calculate the time-dependent contribution of particles to any given spatial cell. And then what we can do is we can convolve that with the measured alpha flux to compute the expected density. So what this plot shows here is what the modeled time dependence is, that time constant, as a function of local time and altitude. And so we get values that range from 3 to 12 days, depending what altitude and local time our measurements are coming from. So here's a plot of what LADEE's observations, what the spatial distribution of those are as a function of local time and altitude. And so Mehdi Bena's paper that was recently published in GRL took the helium observations from near the Dawn terminator and fit them to an ARTEMIS flux. Those came from right here. He used a time decay of 4.5 days and got an excellent agreement. So this matches nicely with what the model is predicting the effective time constant would be in that region. Now with LAMP, our observing geometry is such that we're looking at this illuminated column when we're on the night side and the foot point of the measurements in the dark. So we measure whatever's above the shadow and between the spacecraft and that shadow line. So as a function of latitude, because we're going through different latitudes, this is the altitude range that we can see for different local time bends. So what you can see is that when we are near the terminator, we're seeing through a long column and a long latitude range. Oh, thanks. And so when we're very close to midnight, we're just seeing this section here. So it's really complicated because our observations cover quite a range in expected time decay. So I used my forward model to model what that actually would be with the measured out the hourly alpha flux, and this is what I get. One thing I think that we can say is that this 1-to-1 is ruled out, so that it's not 100% solar wind being thermalized and being re-emitted into the exosphere. So we have an intercept that yields about a 41% background source. That background may be endogenous helium, or it may be solar wind helium that is implanted and diffuses out more slowly. The slope being less than 1, that shows it's about 50 or 0.5. That's showing that about 50% of the alpha particles are responding promptly and going immediately into the exosphere, and the other 50% are either being lost, and then you would have this being completely endogenous helium, or that 50% is being implanted and is slowly diffusing out, and then this would be the slow diffusion of solar wind. So those are our conclusions. The transport time and the apparent escape rate of helium varies as a function of latitude, local time, and altitude. And that when we use a time-dependent model, it improves our fits between the ARTEMIS data and the LAMP or NMS data. And that the dynamic range of the LAMP measurements is a lot smaller than what the model says you can do with a prompt response of the solar wind. So either there's some systematic error going on, or that the solar wind is participating in this slower diffusion process, which is creating kind of a background contribution of about 41%. Or the solar wind is being lost, and you have this endogenic source going on. So thank you very much.
John Keller, Goddard, Dana, I wonder if you want to consider the velocity of the helium, because that will change the degree of implantation or the degree of direct reflection of the helium on the surface, and might play a role in some of your observations.
Yeah, I mean, that's interesting, and that's something that we can look into a little bit more. Yeah, I know that there are going to be differences as a function of latitude that we haven't even looked into because of the temperature dependence of the diffusion time and that sort of stuff. So there are more things we can do to try to figure that out.
Hey Dana, Carl Hibbs, APL. Nice talk, and you cover a lot of ground, so I'm just going to ask a clarifying question. So if the helium is diffusing, do you mean diffusing out of the grain, or do you mean diffusing within the regolith slowly? And there's so those would be two different diffusion processes, one out of grain, one between grains.
Right. So for the helium, or for the solar wind component, it would be diffusion out of the grain. So it gets implanted, you know, some tens of nanometers in, and it would take some time to diffuse out of that grain. For the endogenic source, the radiogenic helium, it would be diffusing out of the, you know, bulk of the moon.
Okay. Okay.
Derek Sears, NASA Ames. If I'm understanding you correctly, you can calculate the amount and the different components of helium in the regolith. Have you compared your calculations with the measurements we got from Apollo soil?
No, I haven't, and that's a good thing to do. I'll look into that because you know, trying to decide between this scenario and this scenario, then you're going to have some steady state abundance of helium that's implanted into the soil. I'm not sure how well that would last in terms of being, you know, transported from the moon back home to be measured, but it's certainly something to look into.
Right. But you've got a variety of locations. I don't know that they spread very much, but that might be helpful.
Thank you, Dana, for being on time, unlike myself. The next presentation